So in this chapter, chapter 10, the mathematics of population growth, we are going to start by exploring some of the vocabulary and how it's used. Population growth not only refers to human populations, but can be used to address animal populations. It can be used to count the increase or decrease of garbage populations, and so on. The phrase population growth has become very broad in its use. Originally from the Latin populus, meaning people, it was intended for human populations, but now we use it to describe money increasing or decreasing. We use it to describe garbage, animals, and so on. The population growth that we're interested in for this chapter is discrete growth, which you can think of as accountable growth or growth measured over specific intervals of time. Continuous growth is something you would see with compound interest, where you're computing the interest of every minute, of every second, of every day. There's a change in the balance. So we're not dealing with that in this chapter, just the discrete growth. The phrase growth versus the phrase decay used to be that growth was for increasing and decay was for decreasing. Now growth can be used for either. A positive growth is increasing, a negative growth is decreasing, but decay still implies a negative growth. We will represent our populations using sequences. Sequences are lists of numbers. So at the bottom of the screen, we see P0 is the population at time 0, also known as the initial population. P1 is the population after one generation. P2 is the population after 2 generations of growth, and so on. Pn represents the population after n generations of growth or decline. The types of models we will be using are implicit, which uses recursion to calculate the populations, or explicit, which uses functions to calculate the populations. On this slide, the recursive models for linear growth and exponential growth are given. In example 1, it says Pn, which represents the population for generation n, is equal to Pn minus 1. That means the previous generation population. And we add d. D is the linear growth factor for the population between each generation. Example 2 is the recursive model for exponential growth. Instead of adding, we are multiplying the growth rate. So the population of generation n is equal to the previous year's population, or the previous generation population, times r, the growth rate. In this application, you see it says to consider an application that grows according to a linear growth model. That means you would go to the previous slide and choose the formula from example 1, the linear growth model. The initial population is 25. That means you would set P0 equal to 25. And the growth rate is 7 per generation. So you would set D equal to 7. And down below, you see that the linear growth model is Pn equals Pn minus 1 plus D. And we have P0 is 25 and D is 7. So when we're calculating the population for generation 1, you plug in the number 1 everywhere you see n, and you get P1 equals P0 plus D, which gives us P1 equals 25 plus 7. So the population of generation 1 is 32. You can repeat this for generation 2, and you find that P2 is equal to P1. Remember, you always subtract 1 from the generation. We can look up P1 from the previous line, which is 32, and add 7 to it. So we found the population for the second generation is 39. We will go into more detail and depth on how to use these models in the sections that follow.